Then analysis of sway frames, that will be the next lecture, the following one. Example 1, 2, and 3 will cover there, and then assignment 4 part B you will get there. Now starting from the introduction, again, frames are analyzed with stiffness method due to solve the problem in matrix notation, which is more systematic, to compute reactions at all the support reactions, to compute internal resisting shear, axial, and bending moment at any section of the frame. So it's a systematic where you can find out the member and actions, you can find out the support reactions also. Prerequisites, again, it's a repetition of the previous one. You should be having enough concept of matrix algebra, must be able to find the kinematic indeterminacy, and must know the formulas and concept of fixed end actions. Hello. Assalamu alaikum. आज आगे से ज़रूर lecture क्यों मिला? That's why. जमा हो गया रे 1 o'clock तक. Okay. So now types of frames. On the basis of lateral displacement, frames are classified into the following 2 types: frames with sway and frames without sway. Now, sway, what is a sway frame? Now, in kinematically indeterminate structure, instead of statically, it is a kinematically indeterminate structure. The frames deflect laterally due to the presence of lateral loads or unsymmetrical vertical loads, or where the frames themselves are unsymmetrical. Now, to determine whether this frame is having a sway condition or not, you will have to look at these now various parameters, like the lateral loads you will be looking for. If there is a lateral load, then the support condition, it can go sidewise, so it will be allowing the sway. So it will be known as a sway frame. Unsymmetrical vertical loads. If you have unsymmetrical loads, with examples, I'll explain all these situations, or where the frames themselves are unsymmetrical. Now, causes of sway, these are given here in the bullet form. Unsymmetrical loading. If you have unsymmetrical loading, like the loads are eccentric, they are not concentric, so the possibility is that there will be sway. Different end conditions of the columns of the frames. If the end conditions of the columns are not the same, let's say at one side we have a hinge support, but at the other side we have a roller support, or at one side we have a roller support, at the other side we have a fixed support, so unsymmetrical support conditions, then there is the possibility of the side sway. No uniform section, non-uniform sections of the members. The cross-sectional dimensions, they are not the same. The problem with the symmetry, so again you will be having a side sway. Side sway, now what is a side sway? It is the lateral movement of the frame. One is buckling. Now, buckling is the instability of a member, which goes due to excessive stress, due to slenderness. If a member deflects locally, that is known as a buckling. But if the whole now frame goes like it deflects laterally, the whole frame, then that is known as a sway. Horizontal loading on column of the frame. So horizontal loading on column of this can be a now reason for the side sway. And settlement of the supports, unequal settlement of the supports of the frame. Now let's go by examples now. Frame with outside sway. This is non-sway frame now here we are showing. Now at A, if you see, we have a hinge support condition. At B, we have a rigid joint. And at C, again, we have a hinge condition, hinge support condition. If you look at the loading now, the frame is unsymmetrical now. This 5 meters vertical length, if you see, we don't have this on the right side. But the thing is, now at C, it can take the lateral force now, so it means it is not allowing the movement in the horizontal direction. So when there is no displacement in the horizontal direction, it means it is a non-sway frame, which is known as frames with outside sway. This can take the horizontal reaction. It is not allowing the horizontal movement. So the left top diagram I'm discussing now, the support conditions, if you look at the support conditions, these are enough to tell you that it is not allowing any side without looking at the load or other geometry of this problem. Now coming to the right top now, if you see here again at A, which is this left top support, again we have a hinge support. Then at B we have a rigid joint, at C we have a rigid joint, at D we have a pin support, and at E we have again a hinge support, and at D also a hinge support. Now 10 kip. Now if we look at again at the support conditions, at A it can take vertical and horizontal forces, at E again vertical and horizontal, and at D and E, if you see, these are almost rigid because it is not allowing any movement also because of this angle at left and right side. So now if you see, this frame again cannot move now sidewise. It cannot have lateral movement. So again, it is a non-sway frame or a frame without sway. If you look at 2 kip per foot uniformly distributed load distance, so the loading is unsymmetrical. But looking at the support condition, it is not allowing any lateral movement, so it means it is a non-sway frame. Now coming to this bottom left one, at A we have a pin support, B we have a rigid joint, at C we have a rigid joint, at D we have again a pin support. Now if BC, if you see, they can go sidewise, but now if you see, AB member is same as DC member. Support conditions for both the members are the same. Now the horizontal member, if we look at 4 meter, we have from the ends this 18 kilonewton. So we have the member symmetry, we have the support symmetry, and we have the loading symmetry also. It's as a whole symmetrical now beam. So because of this symmetrical configuration of the loading as well as geometry, it is not allowing any sideway movement. So again, it is example of the non-sway frame. Now, the last figure, which is the bottom right one, at A we have a pin support, at B we have rigid joint, at C we have again a pin support now. Although at member AB, if you see at the middle we have rightward directed 4 kip load. This will try to push it to the right, but now at C you see there we have the capability to resist the horizontal force. So it means that it is again not allowing any lateral movement, any lateral displacement. So again, it is example of the non-sway frame. Here you can see now, although the B and C joint at this diagram, which is the left bottom one, B and C joints were free to move, but because of the symmetry of the structure, because of the symmetry of support, geometry, and loading, we say it is not going to go sidewise. So we declare this as a non-sway frame. Now, sway frame, today this will be the topic of discussion. We will be solving problems based on the side sway, non-side sway condition or without side sway. Now coming here now, these are frames now with side sway. The previous slide we were having without side sway, and these are now with side side sway. Now this top left one, if you see, A, we have a pin connection. D, we have a rigid joint. C, a rigid joint. D, a pin joint. And if we look at this pointed load, it is 1 meter from the left side and 3 meters from joint C now. Means the pointed load, it is unsymmetrical now. If you look at the support condition, A and B are similar. If you look at the vertical, AD and BC, the cross-sectional dimension, the height, the geometry is the same. If you look at the DC, it is also again prismatic one. So geometry of the structure, it is symmetrical, but loading is unsymmetrical. So now how it is going to go sidewise? It is eccentric now. If it was at 2 feet, if it was at the center of this DC, then it was a symmetric loading condition, but now it is unsymmetric. So how it is going to sway now? It is going to sway to the left now. The frame is going to deflect to the left this way. If you are following my cursor, so this is going to, by observation even, you can say that it is going to go this way. So this will be creating a sway condition. Now, right top one, A, D, C, and B you are looking at. The structure is not symmetrical. Why? Because AD is not similar to BC, and if you see this 3 kip leftward directed force at joint C, it will cause now the structure to move to the left now. So this will be giving a lateral displacement now, and because of this displacement, we declare this as a side sway frame. So this is a sway frame now. It will be allowing the sway. Coming to the left bottom one, A, D, C, and B we are looking at. At AD, if you see, is not equal to BC now, means the structure is unsymmetrical, although support A is same as support B. But AD, the left vertical member is 18 feet, BC is 12 feet, so this is causing the unsymmetry. And then we have the lateral loading now, 0.2 kip per foot. Nothing is there at the level DC to resist this reaction, so it means it is going to deflect to the right. Like at B, it will be here. At B, the position will remain the same, but it is going to deflect this way, and here it is going to deflect this way. So again, we declare this as a sway frame. It is having a side sway. Similarly, the bottom one, right frame, if you look at the frame is symmetrical. AB is similar to DC, but at BC, if you see, we don't have any support, we don't have any restraint to stop the lateral displacement. So that is why, because of this lateral 8 kip load, we declare this again as a sway frame. So this will be allowing the sway. These were few examples where the sway and non-sway conditions are demonstrated. Now, analysis of frames without side sway. So non-sway frames we will be discussing, and the stepwise solution we will be discussing now in this case. Now, before this, let me ask you if you have any question now, and let me see the number. Why the number of students 23 now? So it means only 19 students are attending today's this class. So what is the reason? CR.
Sir, शायद वो paper.
Can you speak a little bit louder?
Yes, sir.
Noman, what is the reason?
सर मैंने तो कल सबको मैसेज किया था, लेकिन शायद वो 12 तक पेपर सबमिट करने का टाइम है।
अच्छा,
शायद वो पेपर लिख रहे।
नहीं, इसी पेपर का और बाकी भी आप लोगों के पेपर्स होंगे ना, so you should plan your this activity accordingly. It was already understood, and already you spend more than 1 week now in these solutions and these things.
Yes, sir.
Achha, now any question about the sway and non-sway frames? Any question? Mr. Josefa? Do
Yes,
you have
sir.
any question?
Sir, I don't have any questions. No,
Clear?
sir.
Acha, okay. What about Mudassir Ahmed Khan?
Yes,
Do
sir.
you have any question?
No, sir.
Clear what is sway and what is non-sway frame?
Yes, sir.
Okay. Okay, so let's now proceed with this these steps now. So stepwise solution procedure using stiffness method. Now, following steps must be followed. Now, remember, it is exactly the same steps which we used for in case of the beam. So you should not be having any difficulty in understanding these steps now. What we do in step number 1, make the structure kinematically determinate, which we call restraint structure. So once we get the restraint structure, then we select the redundant joint displacement. What is your D1, D2, and D3, and so on. And corresponding to those D1, D2, D3, we look into the actual structure and we look for the external actions. And those corresponding external actions we include in the AD matrix. So this way we make the AD matrix. Second step, apply the actual external loads on the basic kinematic determinate structure and find the actions at the locations of redundant joints, compute the fixed end actions, which will generate ADL matrix. In step number 1, we generate the AD matrix, and step number 2, we generate the ADL matrix. And what is ADL matrix? For the ADL matrix, we apply the actual external loads to the restraint structure, and we find out the corresponding actions to the unknown joint displacements, and those corresponding actions that will constitute the ADL matrix. Step number 3, we apply the redundant joint displacements now on the basic kinematic determinate structure. And as a matter of standardized procedure, what we do, we apply unit action to unit displacement turn by turn. And this way, when we apply to corresponding to D1, that will generate the first column of the stiffness matrix. When we apply corresponding to D2, that will generate the second column, and so on. And this way we generate the stiffness coefficient matrix. Step number 4, then we come and we apply the equilibrium condition at the location of the redundant joint displacement. So we write the equilibrium equations and then we solve them for the unknown joint displacements. If you look at the now equilibrium equation, AD, which we found in step number 1, so we have the quantities. ADL we found in step number 2, we have those numbers. S, the stiffness coefficient, which we found in step number 3, so we have those numbers. The only unknown is the unknown joint displacement. So now we are in a position to find the unknown joint displacements with the help of these already known numbers. So we find the unknown joint displacements. So step number 5, then we go and compute the membrane actions or the supportary actions as you want. So you can find out those one. And then we draw the shear force and bending moment diagrams. Now coming to the actual problem, you are looking at the frame now, a 2 members frame. We have AB vertical member and BC the horizontal member. The problem is analyze the given frame using stiffness method and also draw the shear force and bending moment diagram. If you check here, take EI is equal to constant. If the actual numbers are given, so you will have to use those numbers accordingly. Now AB, the height of this frame, it is 10 feet and BC, the horizontal distance between B and C, it is 12 feet now. We don't have any lateral loading on this frame. At A, we have a fixed support, and at C, we have a hinge support. BC member, this horizontal member, it is loaded with UDL, and its intensity is 2 kip per foot. The first step in the stiffness method is to identify which one joints can have movement. We look for the degree of freedom now. If we look for the total degree of freedom, ignoring, let's say, we are taking into account the axial effects also. So B joint is free now. So free joint can have 3 kinds of now movements. It can have horizontal, it can have vertical, and it can have rotation also. At A, if you see, it is not allowing any kind of displacement. So the degree of freedom at A is equal to 0 because it is a fixed support. B, as we discussed, a free joint, so it can allow all the 3 kinds of displacements. At C now, if you see, it cannot allow the vertical displacement, it cannot allow the horizontal displacement, but it can allow rotation now. So here we have 1 degree of freedom. So at B we have 3, and at C we have 1. So it is 4 degrees indeterminate problem. But now if we ignore the axial effects, it means it cannot go in the horizontal direction, it cannot go in the vertical direction, and we have 2 members there to stop that effect now. So 4 minus 2 now, it is becoming 2 degrees kinematically indeterminate problem. And which one are those 2? Which is rotation at B and which is rotation at C now. So theta B and theta C are becoming our unknowns. Now at the bottom now you can see this note, kinematic indeterminacy of this problem. We declare 2 degrees, and when it is 2 degrees, when we neglect the axial effects now. Now, so 2 redundant joint displacements should be chosen. And which one are those 2? If we go to the next slide now, here you see rotation at B, clockwise rotation, I'm assuming now D1, and clockwise rotation at C, I am assuming this is D2. So these are becoming my unknown joint displacements now. And this is how we call this 2 degrees indeterminate. So step number 1 is selection of redundant joint displacements and assign coordinates at those locations. Also compute AD values. So now when we select these D1 and D2, then we are in a position to look for the corresponding external actions, and those we will include in the AD matrix now. So D1 and D2, here at the bottom you see we declare them as our unknowns. Why? Because rotation at B and C are taken as redundant joint displacements. Now corresponding to D1, do we have any externally applied moment? No, we don't have it. So AD1 we say it is equal to 0. Similarly, corresponding to D2 at joint C, we don't have any externally applied moment. So AD2 we say again is equal to 0. So we have now constructed the AD matrix. Now both are 0. Why 0? Because corresponding to unknown joint displacements, which are D1 and D2, in this particular case, we don't have any external applied action. And which are those corresponding external applied actions? Those are the moments. We don't have any moments. Let's say at joint B, we have a horizontal, let's say a horizontal force of 5 kip, but that is not corresponding to the rotation. To the rotation corresponding action is moment. So we are not going to include that 5 kip as a AD1 because that is not, although it is at the B location, but that is not corresponding to D1 now. D1 is rotation, and the rotation corresponding action is moment. So with this much explanation, now let me go to step number 2 now. And now before going to step number 2, let's make this as a determinate structure. So kinematically determinate, how we make it, we restrain the degree of freedom now at B. What we do, we put a fixed support. This is just to show like this is fixed now. So this is just, you are looking at inclined, you can make it vertical also, we can show it horizontal also, but this is, and at C again, if you see the hinge support, we have made it now the fixed support again. So each member, and if you see, we have clamped, we have made it fixed. Now here, what we are restraining at B we are restraining moment. We are restraining rotation. We are restraining what here? We are restraining rotation. And at C, what we are doing? We are restraining again rotation here. So it means it at B, if we talk about how only rotation we can restrain here, if we allow translation, let's say in the vertical direction, so we will have to provide actually a roller guide here. A roller guide here. So that will give you that situation where you are restraining the moment only. So this is now the picture of the basic kinematic determinate structure. Now, with this now, what we do, we apply externally applied loads, the actual loads now to this structure. So at B we have split all the, at B you can see it's a fixed support. So at joint B it's again the same fixed support. At AB there was no load. At BC there was a UDL of 2 kip per foot. BC was 12 feet, so you can see that information here also. And AB was 10 feet, so you can see that information here also. Now at BC, if now we are finding out the member and actions now. So WL square divided by 12, that is now from the fixed end formula now, fixed end actions formula. And it is coming 24 kip feet. Similarly at C also again WL square divided by 12, so it is again 24 kip feet. The vertical reaction which we will need for the member and actions now, it is WL divided by 2. So WL is 24 times 12 divided by 2, 12 kip and 12 kip. Now coming to this one, member AB, we don't have any lateral load now on this one. So 0 moment at B and 0 moment at A also. No shear because we don't have any now lateral load on this one, so shear. Now from where this 12 is coming, this 12 is actually coming from this B joint, and that is why I told you that we are stopping here the moment now only, the rotation here only. So it means that when the rotation will be stopped, when it is capable of taking the whole moment now, but still it can slide in the vertical direction. So this, because of the sliding, what will happen? This 12 kip is going to shift now to this B support now. This 12 was in upward direction, so it is going to be balanced by this 12 kip in the downward direction, and eventually it will now flow to the this support A where we have the fixed support now. So this 12 kip is in the upward direction. This moment is not going to transfer here. Why? Because we have fixed this support because of not allowing the theta now. Similarly here now we have these ones, so already we have a fixed support here, so it is taking the moment and it is taking this load also. Now to make the ADL matrix at joint B, we need to add up whatever is corresponding to D1 now. So to the D1 is first this action which is 0. And then we have counterclockwise 24 kip feet. So it means it is 0 minus 24. Why minus? Again, it is not corresponding to the D1 direction. That was clockwise direction. It is opposite to that one. So minus 24 kip feet. So minus 24 plus 0. So ADL1 here we write minus 24 kip feet. Corresponding to D2 at this coordinate 2, we have a clockwise movement of 24 kip feet. So ADL2, it is becoming our plus 24. And this way we have now completed the ADL1 and ADL2 matrix, minus 24 and plus 24. Now let me go to the question sessions now. You can turn on your mics and you can ask me if you have any problem with finding these ADL matrix. Yeah, Mr. Faraz. Ahmad Faraz, do you have any problem? Any question? Mr. Noman,
Yes, sir.
can we move?
Yes, sir. Sir, ये minus 24 की समझ नहीं आई.
I cannot
zero
hear you,
minus
Mr.
24.
Noman.
Yes, sir.
Hello?
Hello. सर आवाज आ रही है?
Noman, आपकी आवाज नहीं आ रही. Can you are you asking me any question? Are you asking me any question, or can we move now?
Yes, sir. Move करें sir.
अच्छा, move करें. Okay, so we are going ahead now. Okay, so this is how we construct the ADL matrix. Now we are going after the stiffness coefficient matrix now. So step number 3 is primary structure acted upon a unit value of D now, and computation of stiffness coefficients S values in the basic kinematic determinant structure corresponding to the redundant joint displacement locations. So first, a unit rotation is applied at location 1 and prevented at 2 as shown. And this will generate the first column of the stiffness matrix, which will be S11 and S21. And then what we do, we apply a unit rotation at the redundant displacement location 2 and prevent it at 1 as shown, and compute the values of the second column of the stiffness coefficient matrix, which is S12 and S22 now. So first let's keep now D1 is equal to 1 and D2 is equal to 0 here. If you see here now, at 1, what we are doing, we are giving this clockwise rotation. If you see how the rotation is measured, starting from the original member to the deflected form. Now to the deflected form, this down one curve, if you see, this is the deflected form, and this green line is tangent to this deflected shape. So theta is equal to 1 is actually this rotation now, and if you see the sense of this rotation, it is clockwise. And if it is now how the member AB is going to deflect, it is going to deflect this way. Why? Because it's a rigid joint, and originally if you see, the members were making 90 degrees, and after deflection it will be making again 90 degrees. That is the definition of the rigid joint, that after deflection the angle are these angles, they will rotate by the same angles. Now clockwise here, if you see this member AB, again the rotation starting from the original member now and touching to the tangent to the deflected shape, it is again clockwise. Now again we are using the same principle now. At the near end, because of this rotation, action, which is moment here generated, will be 4EI divided by L. At the far end in the same direction, it will be 2EI divided by L. The balancing couple will be, it was clockwise, and how much was the unbalanced moment? 4EI over 12 and 2EI over 12. So 6EI over 12 divided by length, that will give you the magnitude of the balancing couple now. So 6EI theta or L square. What is L? It is the BC distance now. That 12 is given here. So 4EI over L, 2EI over L. Here we have the reaction in the downward direction at B for member BC. So that is 6EI over 12 square, and here it is in the upward direction, 6EI over 12 square. Again, how we are treating this BC, we are treating this as a beam, which we did in case of the beams. So this BC is going to be in the downward direction. Now taking member AB now, again the rotation, this is the near end, so the moment generated here will be 4EI theta divided by L. Theta is 1, EI is constant, 4 is here, and L is how much the vertical now, 10 is given here. This is the height of this member. So 4EI divided by 10. Now at the far end, moment will be in the same direction. So again you see the clockwise. Why? Because the rotation was in the clockwise. So moments generated will be in the clockwise direction. This is 2EI divided by 10. Now clockwise unbalanced moment for this member AB we have. So we need to balance this with the counterclockwise couple now, and this will become 6EI theta divided by L square. So here you see the balancing couple now, and you see a sense also it will cause counterclockwise, which is the balancing moment in this case. Now shear and moments we found, but now from where this 6EI or 12 square is coming, again if you remember at this B joint we were restraining only the rotation, means it was not capable to transfer the moment, but still it can transfer the shear and axial forces. So here if you remember it was downward 6EI over 12 square. So for member AB to balance this joint, it will become in the upward direction 6EI over 12 square. And for this member to keep the member in equilibrium, it will become 6EI over 12 square in the downward direction. Similarly here, 6EI 12 square for member AB at joint B, it was leftward directed. So for the same joint for member BC, it will become rightward directed now, this 6EI over 12 square. And how it is going to be balanced for this member, which is 12 feet length? It will be balanced now in the leftward direction, the same amount, 6EI over 10 square. So here the horizontal reaction, it is leftward directed, and magnitude is 6EI over 10 square. It is not shown, but it is here. Now this is when we keep D1 is equal to 1 and D2 is equal to 0. Now let's start now making the S11 and S21 now values. So what will be S11? It will be the summation of moments now at this joint A corresponding to D1 now. If you see D1 was clockwise, so this 4EI over 12 is in clockwise direction. And then we have again at this B from this member AB a clockwise moment of 4EI over 10 now. So S11 now is becoming equal to 4EI over 12 plus 4EI over 10. And what will be S21 at S at 2 due to 1, it will be 2EI over 12 now, this moment. Although we have three reactions now, three reactions at 2, but corresponding to the D2 is this moment now, which is 2EI over 12, and it is clockwise, means in the direction of the D2. So we will take this plus now. So this is how now S11 is equal to 4EI over 12 plus 4EI over 10 as we discussed. And if we write this in decimal, so this becomes 0.733 EI. And S21, as we said, it is 2EI over 12, so it is becoming 0.1667 EI. So the first column of the stiffness matrix is generated. Now we will generate the second column of the stiffness matrix now, and how that will be generated. Corresponding to D2, we will give a unit rotation, and rest of the places we keep them fixed, we keep them restrained. So here now you see, let's see what we do now. Here we give a unit rotation. Here you can see this theta is equal to 1. Which one? In the direction of D2 now, which was clockwise. So clockwise here, if you draw a tangent, so theta is equal to 1 we are given. As it is, and here at B now you see at D1 location, what we are doing, we are keeping it fixed now. As a matter of fact, here we should be showing this support also rotated by this theta is equal to 1. So we need to make it inclined to the right because we are rotating it in the clockwise direction. Now this 2 coordinate, it is corresponding to D2 now, and it is becoming the near end. Why near end? Because we are applying rotation here. So 4EI theta over L, that will be the moment generated here. So 4EI, how much is L now? L is this 12, so 4EI over 12. This is becoming our far end. So the same clockwise direction, 2EI over 12, half of this moment now we are applying. And what will be now the balancing couple? It will be 6EI theta divided by L square. And how we find its direction? It should be creating a balancing moment to this balanced one. Unbalanced one was clockwise, so the balancing one should be counterclockwise. So here this reaction will be in the downward direction, and here it is in the upward direction, and 6EI over 12 square is going to be the magnitude. As we are restraining rotation here only, so this 6EI over 12, which is in downward direction for member base BC, for member AB at joint B, it will become in the upward direction. Why? Because to keep this B joint in equilibrium, and to keep this member AB in equilibrium, it will be in the downward direction. Why? Because at B it was in the upward direction, so at A it is becoming in the downward direction, 6EI over 12 square. Coming to member AB now, here we are not applying any rotation, any translation, so means no member end actions will be generated here. So means this horizontal balancing couple is 0, and the member end moments are also equal to 0. So this member AB in this case will be having only this axial force, which is 6EI over 12 square, which is coming as a result of the vertical reaction from member BC now. Now coming to the formation of S12 and S22. Where will be S12? It will be at 1 due to 2 now. And how much is that now? Corresponding to D1, we have this moment generated, which is 2EI over 12. And if you see, this is exactly the same which we have for S21 now. For member BA is not contributing. So it means 2EI over 12 plus 0. So that is becoming our S12. And what will be S22 now? S22 will become this corresponding action to D2, which is 4EI over 12. So we have now 2EI over 12. You have S12 and S22 is equal to 4EI over 12, and you can see them in the decimals also. So we have all the 4 components of the stiffness coefficient matrix now. So next now we write them in a regular form now. You see the matrix now. S is equal to EI. Why EI? Because we took this common out. It was with each and every component now. And this is the stiffness coefficient matrix. In step number 1, we found the AD. Step number 2, we found the ATL. And step number 3, we found the stiffness S matrix. Now the only unknown in the equilibrium equation, we are left with the unknown joint displacement. So what we do, we now put these values in the equilibrium equation. Here you see the standard form of the equilibrium equation for a 2 degrees kinematically indeterminate problem. These are the linear equations. now followed by the stiffness form, this matrix format, and then the condensed format, and here rearrangement, how we find out the unknown displacements then. So what we do now in the next slide, we are going to put the stiffness matrix here, AD values and ADL values here. So here now you see this is the matrix format. We put the values. If you remember, it was EI times these numbers, but we took the inverse of EI, so it now became 1 over EI. And this is the matrix now for which we need to take the inverse. AD1 and AD2 were 0, 0. ADL1 was minus 24. So this is how you see now. This minus is in the original equation, but this minus is coming with the ADL value. So we put this with the original sign now, which is minus 24. And here it was plus 24. So still it is plus 24. D1 and D2, it is now becoming 55.40 and D2 is becoming minus 99.741. Now the negative sign, this negative sign shows that our assumed redundant joint displacement direction is wrong. It is not in clockwise direction, means it is in the counterclockwise direction, and which makes sense also. If we go through the deflected shape of this one, let me go back this here. Look how it is going to deform now. It is going to deform this way. If you are looking at the cursor, if I follow this, it is under the load, it is going to deform this way. So if we draw a tangent now here to the deflected shape, so it means it is counterclockwise, it is not clockwise. So at C, now the member will deflect now. If we draw a tangent to this, it will be in the counter. What we assumed in the previous case, we assumed that it is deflecting in this shape in clockwise direction, but it is not clockwise. And the final answer is now telling you that your original was wrong. So what we do, we just reverse the direction. Now, coming to the member and actions now, the joint displacements are now theta B is known and our theta C is also known now. Now we should be able to find out the member and actions now. So let's now, we take first member AB, which is the vertical member. It's a frame now, so at each end we should be having three kind of actions: axial, shear, and the bending moment. Here you see axial, this is shear, and bending moment. And how we do its numbering, preferably now you should follow an order now so that you are organized. And when you go to the next pages, so you should be able to see what this number is corresponding to and what is your positive direction. Each and every number you should not be now looking at and matching it, whether I should take it positive or negative. So what I do, I start with the vertical, followed by horizontal, and then followed by moment at a particular joint. And for the now upward, rightward, and clockwise, these are becoming, I'm assuming them as my positive signs. Here, if you see, vertical is AM1. To the right now, AM2, it is rightward, and the moment is clockwise, AM3 now. If we go to giant B now, AM5, now AM4 again vertical, followed by horizontal, and followed by the moment. Now, again, you see the positive directions: upward positive, rightward positive, and clockwise positive. These are now my reference positive directions now, and these are the member and actions also. So accordingly now I'll be picking my values for the AML1, AML2, and so on, and similarly for the AMDs also. These are, now this is my reference line. With this now I take my positive directions. Now, how to pick now our AML values? This is, if you see, this is now coming where we subjected this structure to the actual loading. So AML1, AML2, AML3, AML4, AML5, and AML6 now you see, and positive directions also you can see. Now you need to go back now to from where we generated our ADL matrix. And this 10 feet AB with these member and actions, it is coming from where we generated the ADL matrix. Now corresponding to this AM1, which is AML1, we have plus 12. AML2 is equal to 0. AML3 is equal to 0. And here in the matrix form, we are writing those values. Similarly, AML4, if you see, it is minus 12 now. Why minus 12? Because upward is my positive direction and it is in the downward direction. So this is minus 12. AML5 is 0 and AML6 is also equal to 0. So for member AB, now we have completed the AML matrix. Let's complete the AMD matrix also for this member AB. So member AB, now AMD matrix we are completing. And these are now looking again to that AMs now, you write down the AMDs accordingly. AMD 1, 1, AMD 2, 1, 3, 1, 4, 1, 5, 1, and 6, 1. And this member now for member AB we are doing it. So AMD 1, 1, if you look at it is minus 6 EI over 12 square now. Why? Because it is in opposite direction of this AMD 1. AMD 2, 1, if you see, it is 6 EI over 12 square. AMD 3, 1, if we see, it is 2 EI over 10. Clockwise, this is also clockwise, so this is positive. AMD 4, 1, if we see, so it was in the upward direction here. Why? Because for BC it was in the downward, so here it was in the upward direction with this 6 EI over 12 square. So we include AMD 4.1 is equal to 6 EI over 12 square. AMD 5.1, here we have minus 6 EI over L square, minus 6 EI over 12 square. And AMD 6.1, how much is that? That is 4 EI over 10. So this way we complete the first column of the AMD matrix. And from where this picture is coming when we apply D1 is equal to 1 and D2 is equal to 0 for the generation of the first column of the stiffness matrix. This is the same diagram, and from there we are picking only the AB member now. Similarly, now to complete now the second column of this AMD matrix, what we do now corresponding to D2 we have applied. And again, we are coming to this member AB now. So this is AMD 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, and 6, 2. Now, how much is AMD 1, 2? It is minus 0.0417. AMD 2, 2, it is 0. AMD 3, 2, we don't have any moment, so that is equal to 0. AMD 4, 2, it will be in the upward direction, this 0.0417. AMD 5, 2, we don't have any horizontal, so that is equal to 0. AMD 6, 2, we cannot take this one because this is for member BC. This is not for member AB. So this moment here, corresponding moment to AMD 6, 2 is equal to 0. So we put this equal to 0. And this way we complete this diagram for member AB. For member AB, we have generated AML matrix, we have generated AMD matrix, and we have the unknown joint displacement. So now we can put this in this equation. This is AML values from here. This is AMD values. AD already we found. These were with 1 over EI. These are with EI, so EI is going to cancel with this 1 over EI. That's why finally we don't get any EI values and we have the solid numbers now. So AM 1, 2, 3, 4, 5, 6 now. It's now the multiplication, the product of this, and then addition with this one. Finally, we get these results now. Here now, look. Initially, we have assumed your direction vertical, so it means it is 13.8 is in the upward direction. Adjoint A. This 3.3, it is in the rightward direction, and 11.1, it is in the clockwise direction. Adjoint B now, this is in the down, 13.8, it is in the downward direction. This 3.3, it is leftward directed now. And 22.2, it is again in the clockwise direction. And we put them on now member AB now. You see, it is in the, and this 13, this is again 13, not 13.3, it is 13, it should be 13.8. This should be 13.8 and 13.8. So it should be matching there. So it means this is also 13.8. Have to make changes because the member should be in equilibrium. The share you see, and look, as I said, both moments are in the clockwise direction, so both are in clockwise direction. Within the member, we don't have any now load, externally applied load, so very easily now you can write shear force and bending moment diagram. This is the shear force. Because of 3.5, we are coming to the right. We don't have any loading in between, so it is constant straight, and because of this 3.3, we are coming to the left now. So this is how we complete the shear force diagram. Bending moment diagram, because this 11.11, we are coming in this direction, so means the outer will be in compression and the inner member will be in tension. And similarly here, because of this 22.2. So this is the standard procedure now when you have the member and actions and loading, how to draw the shear force and bending moment diagram. So this way we have completed member AB now. Completely we have analyzed this, we have found its member and actions, and we now just completed drawing this shear force and bending moment diagram. The same procedure now we will have to now repeat for member BC. So for member BC now again, look, let's the axial I'm taking now AM1, this is AM2 followed by the moment, AM3 arbitrary, whatever numbering you want to go, you just fix its labels now. This is horizontal followed by vertical and then the clockwise. Again at C, again horizontal followed by vertical and then the clockwise, and correspondingly now you will be now selecting your AML values and AMD values also. But again, if you see upward, rightward and clockwise, we are now taking the positive values. Now for the AML values, which is here, I'll be going again from where we generated the ADL matrix. So we will be moving to that one, and this is now that 2K per for this and the fixed-ended beam. So horizontally, if you see now, horizontally we don't have any now action corresponding to AML1 and corresponding to AML4 also. So 0 and 0 we are putting at those locations. Corresponding to AML2 we have plus 12, so here you see plus 12. Corresponding to AML3 we have opposite, so minus 24. So this minus 24 is here. AML4 already we discussed. AML4 we don't have anything, so it is 0. AML5 we have 12 corresponding values, so 12 we are writing, and AML6 again clockwise 24, so we have plus 24 here. And for member AB now we have, for member BC now we have completed the AML matrix. Coming now to the AMD matrix now. So AMD matrix. I'm coming now. So I'm going now to the diagram. You don't need to redraw this one now. Again, we have this situation already for generation of the stiffness matrix. We discussed this, but these are now our AMD 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, and 6, 1. And by completing these values now, you will complete the first column of the AMD matrix. So how much is AMD 1, 1? We are dealing with member BC now. So AMD 1, 1. Now, can somebody answer me how much this is going to be? Let me ask you this question now. Mr. Noman, any idea?
Yes, sir.
नोमान, आपकी आवाज नहीं आ रही। What will be AMD 1, 1? Should we take this value 6EI or 12 square?
Yes, sir.
No, लेकिन ये तो है ना, ये ए बी मेंबर के लिए है ना, बी के लिए तो वो उसकी तरफ हो जाएगा ना, बी सी की तरफ, क्योंकि जॉइंट आपने इक्विलिब्रियम करना है। अगर ये आप लेते हैं इसी तरह तो फिर तो ये आपका नेगेटिव आएगा। AMD 1, 1 आप समझ रहे हैं ना, ये आपका नेगेटिव आ जाएगा फिर। लेकिन BC मेंबर पे क्या है, ये राइट वर्ड डायरेक्टेड हो जाएगा, तो इसका डायरेक्शन BC मेंबर के लिए क्या है, वो पॉजिटिव हो जाएगा, क्योंकि वही AMD 1, 1 की डायरेक्शन में हो जाएगा। AMD 2, 1 क्या होगा, यहाँ पे डाउनवर्ड डायरेक्टेड आपका 6EI और 12 स्क्वायर जो है वो हो जाएगा। AMD 3, 1 क्या होगा, ये आपका 4EI और 12 हो जाएगा। AMD 4, 1 कितना होगा, यहाँ पे आपका राइट वर्ड डायरेक्टेड है, तो यहाँ पे आपका लेफ्ट वर्ड, तो ये माइनस जो है ना, ये 6EI और 12 स्क्वायर हो जाएगा। AMD 5, 1 कितना होगा, 6EI और 12 स्क्वायर। AMD 6, 1 कितना होगा, ये आपका 2EI और 12 हो जाएगा। सिमिलरली नाउ द सेकंड कॉलम आप कैसे जनरेट करेंगे, जहां से आपने स्टिफनेस मैट्रिक्स का सेकंड कॉलम आपने जनरेट किया हुआ था। अब इसमें क्या होगा, आपका AMD 1, 2 क्या होगा, यहाँ पे है ही नहीं आपका इसका करस्पॉन्डिंग, तो इसका 0 हो जाएगा। AMD 2, 1 कितना होगा, यहाँ पे नीचे डायरेक्टेड जो 6EI और 12 स्क्वायर है वो हो जाएगा। AMD 3, 1 क्या होगा, 2EI और 12 हो जाएगा। AMD 4, 2 we don't have any horizontal, so that is 0. AMD 5, 2 कितना होगा, 6EI और 12 स्क्वायर, और AMD 6, 2 कितना होगा, that will be 4EI over 12, and this way we complete this AMD matrix. When this is completed now, we can write now the equilibrium. आपका जो equation है इसको आप लिख लें, ऑलरेडी है आपके पास D1 और D2, ये आपने जनरेट किया, ये भी है आपके पास, and this way now AM1, AM2, AM3, all these values we have, and finally we put them on the, यहाँ पे आप put कर लें, ये लोड है आपके पास, तो ये देखिए 22 पॉइंट, बट काउंटर क्लॉकवाइज हमने किया हुआ है। why counter clockwise? Here you see there AM3 it is coming minus, so because of minus we have reversed its direction, so वो काउंटर क्लॉकवाइज हो गया। अब क्या है, ये सारा आपका लोडिंग भी है, इससे आप क्या कर सकते हैं, मेंबर इंडेक्शंस भी है, इसका लेंथ भी है आपके पास, तो इससे आप इसका शेयर फोर्स और बेंडिंग मोमेंट डायग्राम ड्रा कर सकते हैं। ये उस -22 की वजह से आप माइनस पे आ गए, प्लस आप इससे मालूम कर सकते हैं जहाँ पे आपका शेयर 0 हो रहा है वो डिस्टेंस मालूम कर ले। कैसे मालूम करेंगे, इट विल बी शेयर डिवाइडेड बाय द लोड इंटेंसिटी, जो कि यहाँ पे किया हुआ है। सो दिस इज द रेगुलर स्टफ नाउ के कैसे आप कर सकते हैं। यहाँ पे आप देख लें फर्स्ट डिग्री, वाई बिकॉज वी हैव अ यूडीएल इज कांस्टेंट, सो इट विल बी वेरिंग विद फर्स्ट डिग्री। यहाँ पे फर्स्ट डिग्री, तो यहाँ पे आपका सेकंड डिग्री हो जाएगा बराबर। एंड दिस इज नाउ the shear force and bending moment diagram. After this, now you can draw your combined shear force and bending moment diagrams. Now turn on your mics and ask me if you have any questions. Mr. Abid Ali, do you have any question?
No, sir.
Clear?
Yes, sir. Clear, sir.
Mr. Shahab Masood,
No, sir.
Muhammad Hassan Khan.
No question, sir.
Okay, clear? Mr. Muhammad Mansoor,
Clear, sir.
clear?
Yes, sir.
Because rest of the two problems I'll be going quickly now. So if you have any procedural or anything, problems or any clarification, so you can just ask me. Otherwise, what we do now, we will take a break, and after 20 minutes break now, you can come and you can join the class again, and we will go for rest of the two problems.
Okay, sir.
Okay, so now we start the break now. According to my clock, it is 12:15 now. So you should be back by 12:35. Okay, we'll join again at 12:35. Thank you so much for now.